let's continue on from the last section with our goal of building a very principled foundation of what we mean when we say we're trying to do machine learning. So in particular, in the last section, we talked about concepts very much in general, where we just had some arbitrary set of numbers and we were trying to learn about what generated those numbers. So now let's look more specifically at an example. Let's use the example of a supervised learning problem that we're hopefully more familiar with. So in a supervised learning problem, again, we have a bunch of examples that are drawn from some distribution. But in this case, we have our examples are split into two parts. They have the X, which is what we're going to observe, and Y, which is our label, which is what we're going to try to predict. So our data set is a set of n examples of this pair. And what we would like is we're going to see some new example X, and we want to produce a distribution over Y, our label, given X and our data D. And we imagine that there is some distribution that Y is generated on that depends on X and some parameters theta of some generative distribution. And of course, we don't know these parameters theta. These features X, again, that's what we observe. Generally, this will be X. Each X will be some high dimensional vector. For example, all the pixels in an image. So if X is a M by M image, that's M squared total pixels that are contained within X. Y is the thing we're trying to predict. If Y is simple or low dimensional, for example, cat or not cat, or cat, human, car, or whatever, we tend to think of this as a supervised classification problem. If Y is high dimensional, such as another image or a perhaps a caption to the image that is a full English sentence, then we might call this problem of determining a distribution for Y, we might call that a conditional generative problem. So we already know how to do this. So the first thing we probably need to do is we want a distribution over theta. And to do that, we just use Bayes' rule. So we have, if we plug in Bayes' rule here, we have P of D, that is the probability of our data set overall in the denominator. In the numerator, we have P of theta times P of D given theta. Now, of course, the important term here, or the important factor here, is this one here, P of D given theta. That's the likelihood of our data under a given theta. P of theta lets us put some kind of prior, that is, again, some set of models that we think are more likely than others. And then P, this just normalizes it such that this whole distribution sums to 1. So again, how do we get the thing we want? Here is P of Y given X comma D. That's the information we have. Well, it's easy. We just have to take the integral over all of the possible models. And for each possible model, we multiply together two things. One is P of theta given D from here. And the second one is P of Y given X under that particular theta. So notice that, I said this is easy. It's conceptually simple in that it is just this very short expression. But of course, computationally, to actually do this can be very expensive because in principle, we have to integrate over all of the possible thetas. So even for a simple machine learning algorithm, let's say logistic regression, which we're going to talk about quite a bit, logistic regression has one parameter per feature. So this theta is a vector of m parameters. So we have to integrate over this m-dimensional hypercube. So in practice, because this integral is very computationally expensive to perform, in practice what we usually do is use a plug-in approximation. So this is the same thing we saw just last lecture, but this time applied to the machine learning case. So if we wanted to take the map estimate, that is the maximum a posteriori, that is just the maximum over theta of the probability of theta given our data set, that thing we showed on the last slide. And in practice, we usually take the log of it. I'll talk a little bit why log is a good thing to do in a couple of lectures. And just to break that down a bit, we can break that into two terms. The two terms we saw at the top, the likelihood term, probability of observed data given theta, plus, because of the logs, on the last slide it was multiplied by the prior probability of theta. Notice that the log p of d term, actually not log, but minus, notice that that term went away because all we care about is the maximum over theta. So we don't need to worry about that term. So this equals, we're just going to continue to break this down. What's commonly done is to take the minimum of the negative of this log. Why the negative? Generally, just that when people think about optimization, they tend to think about minimizing something rather than maximizing something. And of course, minimizing the negative of something is equivalent to maximizing the thing itself. So usually, all throughout this course and all throughout the literature, you'll see people minimize a negative rather than maximizing a positive. Doesn't matter. You could do either one. This just happens to be what people like to do. So now we put a negative in both these places. And so this second term has stayed the same. This first term we've split up. This is the likelihood of all of our data. Because of our data set is composed of n independent examples, we've split it up into a sum over n of the probability of yn, again, given theta. Okay, and if we instead are going to use the maximum likelihood estimate rather than the maximum a posteriori estimate, notice that it's exactly the same thing. Here, we're just maximizing the likelihood. That is, we're maximizing that term and throwing away that term. And then, so notice that this thing here is exactly the same. Okay, so this is the plug-in approximation for a machine learning problem. So this is probably something that we're more familiar with. Generally, when we're doing machine learning, we're used to training a model, and by the end, we pick a single model, that is a single set of parameters, which might be the map estimate or the maximum likelihood estimate. I'll talk in a second about what happens if we don't do that. So one way to think about what we're doing here is after we see our data, we end up with some distribution over the possible values of theta. Now again, remember that theta is probably some multidimensional vector here, but I'm just drawing it in one dimension just for simplicity. When we take the map estimate, we're kind of pretending like that distribution is just a extremely high peak over just a specific value of theta. That that shape of posterior, by the way, is called a delta function. So delta, the delta function, it has a infinite value at exactly the specific value of theta and 0 everywhere else. The delta function has the funky mathematical property that the integral of the delta function, that is the integral of delta of theta d theta, equals 1. So that's not very important. Really, what we're saying is just that we've picked the specific value theta hat. But if someone asks you, what distribution do you have over theta, you can say, okay, I've got a delta function. It has only any positive value over the specific value of theta we picked. Okay, so this has all been very abstract. So let's make it a bit more concrete. Let's use a logistic regression model as an example. And again, we're going to go into more detail about logistic regression later. And in fact, let's use a super simple logistic regression model, which is just a single input parameter, or input feature rather. And specifically, the input feature we're using is, or the prediction goal is, we're predicting what species of iris a given flower we're looking at is, and our feature here is the sepal length of the flower. This is apparently some kind of flower anatomy. This is kind of a famous example machine learning problem. I don't know why this became famous, but that's okay. So our model is, again, we're going to imagine that there's some distribution for what the label is. In this case, y can either be 0 or 1, two different types of iris flower, and we're given, for a specific example, x, and unknown, so again, this is unknown, the value of theta, and that we imagine that this distribution is a logistic function with input b plus wx. And that logistic function is this thing. Again, we're going to talk about this in a bit. The logistic function for a particular value a is e to the a over 1 plus e to the a. So just to be clear, our theta vector consists of two values, b and w. Okay, so if we do this, and here's some real data of flowers. These are two types of irises, the orange one and the purple one, and here are their sepal lengths and what the species of flower is. And so if you predict, if you train a model, you might get a distribution like this. Here's our theta hat MAP. And that gives us some distribution. This thing here is the shape of the S shape of the logistic function. And this black line here is the distribution where the function crosses 0.5. So what advantage of taking this this kind of Bayesian approach is that we can also understand the uncertainty in the parameters themselves. That is, here we've picked the MAP parameters, but of course there's some uncertainty in that. So if we actually figure out what is the distribution of values of theta, we might get something like this. This sort of a shaded area indicates the amount of uncertainty in theta that there is given d. That is, p of theta given d isn't super sharp around theta map, but it actually has a little bit of uncertainty. And then here is the uncertainty around that threshold line. And then if we were to actually plot P of y given x it would look something like this, where, and I exaggerated this a little bit, and you can see my drawing skills aren't great, but the curve would be more shallow. That is, it has more uncertainty. You can see here, it's the map curve is very certain about what the label of this this x is, whereas if we're taking into account the uncertainty in the label, we're going to get a little bit uncertainty in the parameter. Sorry, we're going to get a little bit more uncertainty in the label once we calculate the p of y given x. Just to be really complete here, x comma d, not x comma a specific label. If we're plotting that, which is our posterior predictive distribution, that's going to be a little bit more uncertain than p of y given x, comma, theta hat, our map value. Okay, so this is the end of our section on defining what we mean by machine learning. Now, we started kind of extremely basic, and I think the concepts we're talking about here are concepts that most of us are already familiar with. This idea that to do a learning problem, we start with some data, and then we look at possible parameters of the given model, pick the best one, whether that's the maximum likelihood estimate or the maximum a posteriori map estimate, and then we use that model to go and make predictions for new examples. But hopefully having this kind of very rigorous grounding will help us in the future as we encounter new methods. And in particular, I think it helps us in cases where we're dealing with either very simple or very complex models. And I think it also helps us when we need to deal with either the uncertainty in the predictions or the uncertainty in the in parameters. Uncertainty in predictions come up very often where we're trying to make predictions in some cases where our different choices have very different outcomes. For example, when we're deciding whether to do surgery or not surgery, we have to, really think about, what's the impact to the patient of the sort of uncertainties in what's going to happen with that surgery. We're going to talk a little bit about that later. Another is when we have to deal with uncertainty in the parameters. This is a really big issue, especially recently, as we come up with these more and more complex models, like deep learning models, that are very over-parameterized. That is, we have kind of far more parameters than we could possibly learn precisely. So there's a huge amount of uncertainty left in the parameters. And it's worth thinking in a principled way about what impact that has on our predictions. And that comes up when we look at things like adversarial attacks against machine learning, or the uncertainty in ethics in our predictions, and all those kinds of things. Okay, but we'll end this chapter here.